Hello friends, welcome to this video about the design of the Ripple carry adder and the carry look-ahead adder. There are 5 different ways of designing an n-bit binary adder: the Ripple adder, the look-ahead adder, the select adder, the skip adder, and the save adder. In this video, we will focus on the Ripple carry adder and on the carry look-ahead adder. Let's first see the Ripple carry adder. When we perform an addition by hand, starting from the less significant column, we add the digits of each column. As a result, a carry is originated. In the case of binary numbers, this carry can be 0 or 1. When the carry is 1, this carry is added to the next column to obtain the result, and this process continues successively as long as there is a carry. So, from the least significant digit to the most significant digit, the carry is moving stage by stage. This moving is called a rippling effect, and the circuit diagram that graphically represents this process is called the Ripple carry adder. This is the circuit. So, the Ripple carry adder is the simplest and most intuitive diagram because it models the way we do addition by hand using paper and pencil. Note that each state is made by a full adder. The component that we learned in the previous video. So, as you can see, the carry out of the first stage, the least significant stage, is going as the carry input to the next stage. And the carry out of this next stage is going as the carry input of the next stage, and so on. So, a Ripple carry adder is just a cascade of several full adders, one for each column. As you can see, these are the columns of the addition. A and B are the digits of the numbers to be added. S are the sum of each column. C0 is the input carry. C are the intermediate Ripple carries, and Cn is the output carry. Note that C0 is the carry to the column 0, which does not exist because in an isolated sum, C0 is equal to 0. But normally it is shown in the drawing for notation consistency. In fact, this notation will be useful when we will be talking about subtraction. But the Ripple carry adder, although perfect from the point of view of process, has some disadvantages. First, each full adder is unable to start the addition unless its corresponding carry input is available. And second, to obtain the complete final result, you have to wait until all the carries have been added through the different columns. In other words, you have to wait until all the carries have been rippled through all the columns. Consequently, the overall delay of a Ripple carry adder is proportional to the number of stages. In an effort to reduce the delay and speed up the process, engineers and designers came up with a new approach called carry look-ahead adder. As the name implies, the aim is doing some kind of look-ahead to determine the values of the carry digits in advance. If this can be done, then the total time delay of the adder can be reduced from roughly proportional to the number of n stages to the order of 1, which means in this case the delay time will be constant and independent of the number of stages. They concluded that this constant delay will be possible if somehow the carry bits can be generated in parallel. If we can do that, then all the full adders can carry out their addition simultaneously, and they will not need to wait for the previous full adder to complete its task. This is the basic idea behind the carry look-ahead adder. The delay is reduced, but the trouble is that the hardware complexity increases because the amount of gates required increases rapidly. This is the drawback of this idea. Let's go through the detail of how to implement this idea. First, let's look at the logic table of an addition in a full adder. This is the logic table that we have already seen in the previous video about the full adder. We can distinguish three situations: carry delete, carry propagate, and carry generate. The carry delete scenario is the one delineated in the first square. Note that the output carry is always 0. These are the conditions under which, independently of what is the value of the carry in, the output carry is 0. The carry propagate scenario is the one delineated in the second square. Note that the values of the carry in and the carry out are the same: 0, 1, 0, 1, 0, 1, 0, 1. These are the conditions under which, independently of what is the value of the carry in, the same input carry is propagating to the output. The carries generated scenario is the one delineated in the last square. Note that in this case the carry output is always 1. These are the conditions under which a full adder is generating a carry out of 1, independently of the carry coming from the previous stage. For our purpose, the two last scenarios are the ones used to design the look-ahead strategies. From the carry generate scenario, we can say at least one thing: if A and B is equal to 1, then the carry out is 1. And from the carry propagate scenario, we can say that if the carry in is 1 and A is 0 and B is 1, or A is 1 and B is 0, then the carry out is always 1. Converting these scenarios into equations, we have the carry generate scenario is the function g equal to AB, and the carry propagate scenario is the function p equal to AB prime plus A prime B, which is the same as exclusive OR of A and B. So, g equal to 1 represents the condition when a carry is generated in one stage, independently of the previous stage. And p equal to 1 represents the condition when an input carry will be propagated to the output carry. Combining these gi and pi functions, we can write down the following equation: ci plus 1 equal to gi plus pi ci, which means the carry output will be 1 if either a carry is generated or the propagate function is 1 and the carry input is 1. So, if either of these two things are true, then the next carry will be 1. So, considering these scenarios that we just defined, our strategy is to divide the addition process in 3 steps corresponding to each of these equations. First step, second step, third step. In the first step, from A and B we get G and P. In the second step, from G and P, using the combined equation, we get C. And with C and P taken from here, we get the sum. Because the sum in a full adder is always the exclusive OR of A, B and C. What are the advantages of this strategy? First, with this strategy, to get the sum, we do not have to wait for the successive carries to be generated, because only knowing the digits of each column, A and B, we can calculate the sum. And second, the overall sum delay does not depend on the number of carries. Let's then try to deploy this strategy. Let's first concentrate on the second step, the one using the combined equation. For this, if I unroll the recurrent relations for the carry and for the sum, I have this unroll equation, where I have substituted successively the values with their corresponding combined equation. Note that if you continue this unrolling process till you reach C0, in the last term you will be containing the product of all the p's. And for the third step, if we unroll the expression for the sum, we have the sum equal to P exclusive or C. Now, the question is how to convert these equations into a logic circuit for the computer. To see how, let's take the example of a 4-bit adder. That means a sum of two numbers A and B, each made with 4 digits. The first thing is to write the equations for the 4 bits case and try to find out how many gates are needed. So for example, for a 4-bit adder, these will be the equations of C1, C2, C3, C4, and these the equations of S0, S1, S2, S3. So, as you can see, with these equations we can look ahead and calculate the carries in parallel without waiting for the carries to be generated in series. Therefore, with this strategy, to get the sum, we do not have to wait for the successive carries to be generated. Now, the list on the right are the number of gates required. Let's see how to find them out. In the equations, the sign plus means OR. So, the first equation has one OR gate of 5 inputs. 1, 2, 3, 4, 5. One OR gate of 5 inputs. The second equation has one OR gate of 4 inputs. 1, 2, 3, 4. One OR gate of 4 inputs, and so on. And now, for the terms within the equations, the products means N. So, these are AND gates with 2 inputs. So we need 4 AND gates with 2 inputs. These are AND gates with 3 inputs. So we need 3 AND gates with 3 inputs, and so on. And now, for the sum, we need 4 exclusive OR gates. 1, 2, 3, 4. 4 exclusive OR gates. So, to generate the carries from the G and P function, we need a total of 4 OR gates and 10 AND gates. And for the sum, we need 4 exclusive OR gates. Let's then convert these equations into logic circuit. This is the logic circuit to generate the carries from the G and P functions. As we can see, we have used the 10 AND gates and the 4 OR gates. But this is not yet the complete adder circuit. According to our strategy, we need to add the step 1 in front to generate the G and P functions, and the step 3 at the back to generate the sum S. So this is the complete circuit where we can distinguish the 3 steps. First step, second step, third step. As you can see, this is the same circuit as our three-step strategy circuit, but this time more detail showing the logic gates. This is again the same circuit in a more block format. The block of the half adders to produce the GNP functions, the block of the carry look ahead to produce the carry outputs, and the block of the exclusive OR gates to produce the sum outputs. Advantages and disadvantages. When we presented the strategy scenarios, we already talked about the advantages. But now also, after working with the circuits, some disadvantages exist, mainly when the number of n bits increases, that is, when we want to pass from 4 bits carry look ahead adder to 16 bits to 32 bits or more. So, in this slide, you can find together the advantages and the disadvantages. One main problem is that if we look at the deploying equations, as the number of n increases, the complexity of the carry look ahead equations will go on increasing. So, the number of gates will also increase and it will become increasingly difficult and costly to implement the function. So, let's try to design the 16-bit adder and see what we can do. There are a couple of ways by which we can design carry look ahead adders greater than 4 bits. The ripple cascading design and the two-level design. Let's see an example of these alternatives for the case of 16-bit. This is the first alternative using the ripple cascading design. Designing a 16-bit carry look ahead adder in a single block is impractical, as I have just said, because the equations for the carries as you go up to higher number of bits will become exceedingly complex. The product terms will become larger in size. Number of terms will also become very large, requiring a very large OR gates. So, this diagram is the first alternative using the ripple cascading design. This alternative consists in using as a basic building block a 4-bit carry look ahead adder module just like the ones we have designed. Then, repeating them 4 times, and connecting them in a ripple cascading chain, just like it is done in a rippling along the stages. As you can see, this alternative is a mix of a carry look ahead and a ripple carry adder. Every 4 bits you can do in parallel, but every ripple carry will only be generated after the previous carries are generated. So, unless C4 is available, you cannot start addition in the next module. Unless C8 is available, you cannot start addition in the next module, and so on. So, in this alternative, the carry propagation between modules is still slowing down the adder. Let's see the other alternative, the two-level design. This is the diagram. Here, once again, 4-bit carry look ahead blocks are used at the first level, but the carry for each block is generated at a second level using the carry look ahead logic. So, in this alternative, once the carries C4, C8, C12 are issued in parallel at the second level, the overall chain progresses to the first level. So basically, the carry look ahead logic is implemented in 2 stages. 2 levels of carry look ahead are working together, one on top of the other, generating the carries for each block. So, this combination results in a faster propagation delay. The advantage is that for larger values of n bits, more carry look ahead levels can be added. That's how the so-called fast adders are built in many of the recent computer systems. In summary, the ripple carry adder overall delay is proportional to the number of stages, but the carry look ahead adder overall delay does not depend on the number of stages. With the carry look ahead adder design, the sum do not have to wait for the successive carries to be generated. The basic idea for the carry look ahead strategy is to determine the values of the carry digits in advance using the propagate and generate scenarios. And finally, the carry look ahead strategy can be applied at different levels to increase parallel performance. One example is the two-level 16-bit carry look ahead adder that we have just seen. I hope that on the way along this video you learn how to convert the logic table into equations, how to convert logic equations into computer logic circuits, and how to find out the number and type of gates needed to design the logic from a set of equations. Thank you very much for your attention. Have a nice day. If you like this video, please hit the like button and subscribe for more videos.